Hello everybody, and welcome to the next part of Cenozoic Earth history. So as you can see from this slide, we're going to be talking about the onset of the Ice Age. Now I should point out that when we're talking about the onset of the Ice Age as part of this presentation, we're doing it in a very broad sense. Okay, so we're talking about factors that will, contribute towards the Ice Age, but they are not the cause of the last Ice Age. Okay, there's many factors combined together which led to the onset of the last Ice Age. I should point out that we will not be dealing with something called Milankovitch cycles. Okay, so Milankovitch cycles are cycles to do with the position of the Earth relative to the Sun and the tilt of the Earth. So these are contributing factors as well to the onset of Ice Ages. If you want to know about them, you will find them in the textbook. And you'll also find a pretty reasonable discussion actually on Wikipedia. So, alright, let's get talking about the onset of the last Ice Age. Okay, so around 40 million years ago, we begin to notice a couple of things. We notice first of all there's a decrease in ocean surface temperatures at high southern latitudes. So we begin to see that water temperatures towards Antarctica begin to get colder. We also notice that on a global scale, deep ocean temperatures begin to get colder as well. So what's this telling us? Well, if you remember, we've spoken already about this nice, circulation of water coming from the Indian Ocean, going into the Atlantic and then going into the Pacific. And that helps to keep the Atlantic and the Pacific that little bit warmer than they should be. So what's this telling us? Well, it's telling us that this flow of water is possibly beginning to become a little bit more constricted. So by the Oligocene, about 28 million years ago, we begin to see this flow really slowing down. Okay, so the situation is the flow is very constricted by this point. And by the Miocene, 14 million years ago, the flow has stopped altogether. Okay, and we see this as changes in ocean temperature. And the North Atlantic was especially hard hit by the loss of this warm water. At the same time that this is happening, we have the establishment of the Antarctic Circumpolar Current. And this essentially is a current that rings Antarctica and it essentially separates it from the other bodies of water. And the water in the Antarctic Circumpolar Current is cold, so it helps to keep the climate of Antarctica cold, so it helps to contribute to the Antarctic ice sheets formation. There we go. Okay, so these maps are going to kind of show you generally what was going on. So we have the Eocene over here. So this is this flow of warm water. It's coming from the Indian Ocean, going into the Atlantic, and then going into the Pacific. You will begin to notice, though, look here, the continental shelf of Africa is starting to head towards Europe. This area is starting to get tighter. So the flow will be slowing down. Now, obviously, as we can see over here, the link between North and South America is also steadily establishing itself. Okay, by the time we're in the Miocene, Africa has made full contact with Europe, and the flow of warm water from the Indian Ocean into the Atlantic has been completely cut. Now you'll notice, by the way, that the flow itself as it comes in here would have been focused primarily on the North Atlantic. So that's why the North Atlantic is so hard hit, because all of a sudden all that warm water gone. Now you will notice you do have the capacity to communicate between the Atlantic and the Pacific just about, but that doesn't really mean much anymore. So okay, you can see by 14 million years ago we have these individually circulating bodies of water, each with their own individual climate. And if we come down here and look at this diagram at the bottom, you can see them more clearly. So we have the North Atlantic, the South Atlantic, South Pacific, North Pacific, the Indian Ocean, and the Antarctic Circumpolar Current. Okay, and these are the main circulating bodies of water. Now there are some smaller ones, don't get me wrong, but on the whole these are the main bodies. So by the middle Miocene, about 14 million years ago, we have the Antarctic Circumpolar Current establishing itself, and we see a decrease in global temperature. Okay, and now this establishment of the Antarctic Circumpolar Current essentially allows the Antarctic ice sheet to grow a bit larger, and this of course and this of course will help the colour of the Earth get slightly lighter, meaning more solar radiation will be reflected back into space, so it's going to help cool global temperatures. So we also see a brief warming trend in the Pliocene, so just before the last ice age, and we begin to see glaciers forming in the northern hemisphere around 2.6 million years ago. Okay, so after the Pliocene, and this marks the start of the Pleistocene and the Ice Age. Okay, so in terms of the global climate during the Cenozoic, what do we see? Well, you'll notice that there is a general downward trend. Okay, now there are several periods where we have peaks, where we have essentially increases in the global temperature, so it's not a smooth downward trend, and there are also periods where we have sudden decreases in the global temperature. But on the whole, you can see we have a general downward trend. Now, we'll notice that when we look at this downward trend, we don't have any temperature values. Okay, what we have over here though are the oxygen isotope values, and we can see in general that if the oxygen isotopes are going this way, we have cold weather, so more ice. If they're going this way, we have hot weather, so less ice, which kind of makes sense, doesn't it? So this is how we're plotting this decrease in temperature. We're not getting temperature values, but we're getting a general idea of what the trend was. Okay, so the general trend indicates that during the last 2 million years, the Earth has had at least 20 warm-cold cycles. We know that from the oxygen isotope data. And we also know that there's been a fluctuation in temperature of up to 10 Celsius. What we also begin to notice during this period is we begin to see that there's a shift in local climates as well. And so we begin to notice in the more northerly areas, we notice that areas which are located close to glaciers and ice caps, obviously the temperature begins to drop even more in those areas. And that's going to encourage the formation of ice, and it's going to encourage ice to start growing outwards from these locations. Okay, because if you think about it, if the area directly in front of the glacier is nice and cold, that's going to encourage the glacier to move into that area. So one of the other ways that we can tell and get some idea about what was happening during this time frame is pollen analysis. So we've generally been speaking about oxygen isotope analysis using things from the ocean, but we can also get an idea using pollen analysis of what was happening on land. Now this isn't really helpful in terms of telling us what was happening during the Ice Age, because obviously these areas were covered in ice, so not much help there. But they are more helpful in telling us about when the Ice Age was ending. Okay, it's not going to tell us about the Ice Age, the huge changes in the environment. It's going to give us some kind of hints about what was happening though. So pollen analysis uses pollen grains collected from essentially environments where they will be retained. So environments like rivers, lakes, swamps, bogs, and nearshore marine environments. So we can take sediment samples, and we can essentially wash them until we get the pollen grains out, and then the pollen grains can be analysed down a microscope. So one of the things that we know is that individual different plants have different pollen grains essentially, so we can identify the plant by the pollen grain. So this is information from the Chatsworth Bog in Illinois. So here's an age range, so 14,000 years ago to 1,000 years ago. So what we're going to see is we're going to see changes in the plant life depending on the conditions. So around 14,000 years ago, you can see we have quite a large amount of spruce pollen. Now spruce is a coniferous tree. It's the kind of tree that makes up a large part of the boreal forest. Now this is the kind of forest that you get in northern Canada, northern Europe, northern Asia. Okay, it's made up of lots and lots of essentially pine trees, for want of a better term for them, spruce trees. Okay, and so this is a cold weather forest. And so what you can see happening though around 14,000 years ago to 13,000 years, you can see the amount of pollen is dropping off hard. So this is telling us that the ice sheet is really retreating now. Global temperatures are on the way up. The ice sheet is going to be retreating quickly. and you can also see the same thing happens for this cold weather forest. It's dying back very, very fast, and essentially it's having to follow the glaciers northwards. Now, what we notice is that the spruce trees are replaced by ash trees. So ash is the first tree that forms in a deciduous forest. Okay, so if I was to go, oh, I should point out, by the way, it's also an indicator of temperate conditions. Okay, so colder winters and autumns, but warmer summers and springs. So what this means is, if I was to go to somewhere like the United Kingdom, and I was just take an acre of land, and I just left it completely, left it to nature, the first tree that would appear growing on that land would be ash trees. It's an indicator that deciduous forest has started growing. Now, the ash doesn't last particularly long because it's very quickly outcompeted by both elm and oak. Okay, so they take over pretty quickly, and essentially what we have at this point is we've established ourselves a forest. Now, what we begin to notice is that occasionally the amount of grass increases and then decreases, and that corresponds quite nicely to changes in the amount of oak. So this is telling us at this point that the oak forest is dying back and it's being replaced by grasses. Now, this can indicate a range of different conditions, but one of the conditions it can suggest is a warming in the climate. So, this might suggest that somewhere around 4,500 years ago, global temperatures might have gone up a little bit. Okay. Now you'll notice though that there's then a decrease in the grass, and it's then an increase in the oak that match it. Now you'll notice throughout this entire period we have an increase in ragweed and goosefoot, and these these indicate that we're dealing from we're moving from a kind of very dense forest to a more kind of open, sparse kind of set of conditions. So it's telling us something about the forest development. So down here it looks like we have a very, very dense forest, and then slowly over time you'll notice the forest is becoming more and more open, essentially a bit of a essentially looser configuration, and so there's more grasses in between the trees. So that's what we're seeing, and it's obviously telling us quite a lot. So this pollen analysis, it's pretty good. Now if you combine that with tree ring analysis, then you're really well away. Now the thing about tree ring analysis is tree ring analysis can actually be used to give us solid numbers. We can get solid dates. And tree ring analysis can actually go quite a long way back. Now, one of the things we see from this data is the data indicates a continuous warming period until around 6,000 years ago. Okay, so in general, the climate was getting warmer. So at this point, we begin to see the climate of the northern hemisphere especially become cooler and more humid. And that's going to favour the growth of glaciers, especially valley glaciers, so mountainous areas. Now obviously since then, we've seen the temperature pop back up very, very recently. So the episodes of glaciation occurred during this, the episodes of glaciation occurred during this neoglaciation. Okay, this is the start of the glacial period. No, what am I saying? It's essentially, sorry, I do apologise. I'm getting myself completely mixed up there. This is a small glacial period within the Holocene. Sorry about that. Got horribly confused there. Lost track of my dates. So, how do glaciers actually form? So, during the Pleistocene, we had all types of glaciers: valley glaciers, ice caps, and continental glaciers. Now at the moment we have valley glaciers and 2 continental glaciers. Those are the types that dominate. So at present there's only 2 continental glaciers, but during the Pleistocene, continental glaciers covered 30% of the Earth's surface, and now at the moment it's kind of about 10%, give or take a little bit. And that cover is mostly in the northern hemisphere, in terms of what's on land. It's actually, that statement is completely wrong, isn't it? That's a really wrong statement. Yes, ignore me on that one. Yeah, no, just ignore me. Essentially, we have 2 continental glaciers. Just stick with that. I don't know what I was writing there. What's going through my mind? So these glaciers advanced and retreated several times during the Pleistocene and produced much of the topography formed in the associated glaciated areas. So as glaciers retreat backwards and forwards, it's going to affect the topography of the area. As we mentioned, it's going to grind down the topography in those locations. So at the same time, the cooler temperatures obviously encourage the growth of valley glaciers in mountainous areas. So we're going to see the numbers and size of valley glaciers also increasing during periods of glaciation. So glacier formation is actually a surprisingly simple process. So in areas that receive more snow in cooler periods so essentially we want an area that receives more snow in cooler periods than melts in warmer periods. So you get a net accumulation over time. So once the snow accumulation occurs, the snow at the bottom will be compressed and that will produce ice. And this ice will begin to flow in response to pressure as more snow and ice forms above it. So think about it, as more and more weight is put on it, it will naturally want to start flowing away from that point under gravity. So typically you'll need about 40 meters to make this start to happen. So the glacier will then flow from this zone of accumulation where you get more snow being deposited than is lost, and it will essentially go down into the zone of wastage. The zone of wastage is the area where you lose more ice and snow than you gain in the colder periods. And that's pretty much it. It's a pretty straightforward process when you think about it. So as long as the glacier has a balanced budget, so the losses do not exceed the addition and vice versa, the glacier won't change, so it'll be stable. However, if the budget changes, obviously the glacier will shift. So at the moment we've seen temperatures going up, so that means the zone of wastage has essentially been moving up the glacier. So that means the glacier has slowly been melting away because it's not been maintaining equilibrium. It's trying to, but it hasn't found its equilibrium yet. So here we go. So this is the basic diagram. So we have the zone of accumulation here. This is where we essentially retain more snow from the cold periods than we lose. So we have a build-up of glacial ice here. The glacial ice will flow downstream under gravity until eventually it meets the zone of wastage, where it will begin to melt and it will begin to deposit any sediment that it forms. And of course, if you remember, at the front of the glacier here, we're going to have loads and loads of glacial till being deposited, forming a moraine. Obviously, we've also got quite a lot of water coming off the front of this glacier as it melts. That's going to rework some of that moraine. So it's going to transport sediments away from the moraine, and it's going to redistribute those sediments here in this area, which is referred to as the outwash. So the outwash is an area of sediment essentially redistributed by rivers in front of the glacier. So what are the effects of glaciation? Well, the effects of glaciation are massive glaciers moving over the Earth's surface will obviously reshape it. That's pretty much a given, isn't it? So the previous topography before glaciation is going to take a pretty big hit, and we're going to get a completely different topography afterwards. So it should be remembered that the effects of the Ice Age were not limited to glaciers. So the expansion and the retreat of the Ice Age produced marine regressions and transgressions. Okay. So mass glaciations also drove the aforementioned changes in climate. Remember, the temperate zone got pushed down into what now are dry areas like the Sahara or the southwestern United States. Okay, so there are other situations where areas which were once covered in very, very thick glaciers are currently bouncing back up. Remember, 3 kilometers of ice weighs a lot. That's literally going to push. It's going to cause the crust to warp downwards just due to the weight. And now what's happened is since the glaciers have been removed, that crust has been slowly bouncing back upwards. And that's referred to as isostatic rebound. And so what we're seeing there is the crust bouncing back upwards now the ice has been removed. So the glaciers alone, yes, they cause effects, but there's also several effects which are related to them in a kind of distal fashion. So okay, So what are the landforms which are associated with glaciers? Well, one of the most obvious ones is called the ice-scoured plain. So remember, this is the area where the glacier has acted like a bulldozer. So there is little to no soil. There is subdued topography, so the area is really, really flat. Once again, the glacier's bulldozed away topography. The rocks themselves are polished and striated. We discussed why that is earlier. And there's very poor surface drainage. Well, that's simply because the area is very, very flat. There's no essentially shift in height. So that means no shift in height. That means no gradient. No gradient means the water can't really move anywhere, can it? So the water just sits there. In terms of valley glaciers will form a couple of distinct forms. Obviously, we've already discussed the U-shaped valley, so that's a steep valley side either side, and a relatively flat bottom in the middle, producing that U-shape. It will also produce another feature which are referred to as cirques, and these are small kind of, how can I put it? These are small depressions in the side, of the topography either side of the valley glacier. So if you remember, the valley glacier is limited to a valley, isn't it? There's high ground either side. Now a cirque essentially is a small glacier that forms on this high ground, typically on the sides of a valley glacier. Okay, and the cirque, this is kind of like cirque glacier, will contribute ice to the valley glacier, and the cirque itself will be a bowl-shaped feature that forms. Okay, think of it kind of like a tributary going into a river. That's the same kind of system we have here. Now, obviously, continental and valley glaciers will deposit this chaotic mixture of sediments right at their front, which we refer to as a moraine. So here we go. So this is our situation. So here is our glacier, and obviously when it's pushing over the area, under here it's obviously pushing down the crust to start with. It is essentially acting like a bulldozer. The soil goes, topography gets essentially subdued, gets scoured down, for want of a better way of describing it. The rocks themselves become polished, they have striations on them, and the surface drainage is very, very poor. Okay, and this is what it looks like once the ice has gone. So we have our moraines, we have our very, very subdued topography, and we have water building up on the surface. In terms of the valley glacier, so here's a lovely example of a nice U-shaped valley. Actually, this one doesn't have particularly steep sides. It actually has a bit of a gradient. A lot of the very good U-shaped valleys will have near vertical sides. And this is a cirque, you can see it here. So it essentially forms this bowl-shaped feature. And as you can see, the glacier is coming down here. And there's a very good chance this glacier will actually join a larger valley glacier, which we can't see in the picture. So once again, kind of like a tributary joining a much larger river. So just going back to the ice-scoured plains for a second, here's a couple of pictures. Okay, so this is the ice-scoured plain. This is an ice-scoured plain in Canada, and this is one from Wisconsin. So what can we see? Well, first of all, we can see, look at that topography. It has been planed almost flat, hasn't it? So topography is non-existent. Soil, non-existent. Surface drainage, absolutely terrible. You can see that we have a build-up of water here, can't we? And the question is can you see any rivers? Well, we've got a river here, but apart from that, there's nothing draining these bodies of water. The water just builds up here in any depression that it can. So, that's pretty much it. The water doesn't really escape these areas very, very easily, so it builds up on the surface. That's why, areas like Canada and other in the northern plains in the northern US states that have been affected by glaciation will tend to have quite large lakes associated with them because the water can't go anywhere. It's just stuck there. So in terms of the moraines, well, what do we see? Well, we know the moraine is a build-up of material. We've discussed that. I'm actually just going to go back to the previous picture. So if you remember, when our glacier is melting, it's obviously going to produce quite large quantities of water. And we have the moraine here along the front of it. and the sediment being deposited, which makes the moraine, will be reworked, washed away by this water. Okay, and this area in front of the glacier is referred to as the outwash plain. This is where sediment being reworked by the river is essentially distributed again. So over here we have the outwash plain in front of the glacier. So this area is referred to as outwash. Now if we look at this diagram over here, okay, so this is the diagram. So let's look at where we are. So we are currently in the northern US states. We've got Lake Michigan right here, okay, Lake Huron over here, Lake Erie here, and Lake Superior right there. So that should give you some idea of where we are. Okay, now the other thing we're going to keep an eye out for are the moraines themselves. Okay, remember, the moraine is caused whenever the glacier pauses and deposits sediment. Okay, so there are two types of moraines. The first type of moraine is called the terminal moraine. Now that's produced when the glacier reaches its maximum extent. Okay, that's as far as the glacier ever made it. When it reaches its maximum extent, it deposits a moraine there and it never goes any further. From that point on, the only thing the glacier can do is retreat. So then we have what are referred to as recessional moraines. So as your glacier is retreating, it's not a smooth retreat. Instead, your glacier will retreat for a while and stop, at which point it will form a recessional moraine. It will then retreat again, stop, and form another recessional moraine. Retreat again, stop, form another recessional moraine, and so on. So as it retreats, it will form several recessional moraines. Okay. So what we're going to do now is I'm just going to show you this picture down here. So here's a lovely example. So here's our glacier, and you can see right in front of it there is the moraine. Here is this build-up of material. Okay. Now this picture here once again is showing us essentially an area around Wisconsin, and what we're seeing here is we are seeing the Great Lakes, and we are looking at a geologic map showing glacial sediment distribution. Okay, so let's try and work out what's going on. All right, so in yellow here we have the outwash. So remember, the outwash forms on this front edge of the glacier. So look at where the outwash is located. Okay, now we are then going to look at what's referred to as the end moraine. So these are the moraines that are forming at the end of the glacier. Now look carefully. Look, this is where the moraines are reaching their maximum extent, isn't it? Yes? So these are going to be the terminal moraines for the ice sheet. That's as far as it ever reached. Now look, this also corresponds quite nicely with the outwash plains, doesn't it? Okay? Because remember, the outwash plains is depositing all this undifferentiated stuff, which is here in pink. Okay? So we can see essentially this line here, that's essentially the terminal moraine, as far as the ice sheet ever made it. And these are the outwash plains coming off them. So everything's looking quite good, isn't it? Looks quite reasonable. Now then you'll notice, if you look here, for instance, we have one moraine, followed by another moraine, followed by another moraine, followed by another moraine. So these are the recessional moraines, okay, produced as the glaciers retreating along. Now obviously, as you can quite clearly see here, a lot of this stuff is extremely chaotic. It's very difficult to work out what's going on, but this area down here is particularly nice in showing us these recessional moraines as the glacier is retreating. Okay, so we've already gone and discussed this. So as our glacier retreats, we have our moraine forming. We have our outwash here. You can see it in this picture here. So this is the sediment being redistributed from the moraine. Now, this is our recessional moraine right here. It's actually not a particularly great one, but there is one more type of moraine which we need to discuss, and it's referred to as a ground moraine. So a ground moraine is simply the sediment deposited as the glacier retreats. So as the glacier is retreating and it's moving, remember, if it needs to stop to form a moraine, because it needs to build up sediment. But if the glacier is moving, it can't build up a hill of sediment, can it? So instead, all that happens is as the glacier retreats, it simply deposits a blanket of sediment as it goes. And this blanket of sediment that it deposits as it retreats, when it's moving, remember, is referred to as a ground moraine. Okay, so a ground moraine forms when the glacier is moving, whereas recessional moraines and terminal moraines can only form when the glacier is still. All right, so there we go. Perfect. That pretty much covers, the general, things we will see when we look at glaciers in terms of the morphology. So another thing we need to think about are the changes in sea level that we see. Now remember, changes in sea level are very often associated with glaciation. If we have a lot of glaciers, that means lots of water is locked up in ice, and so the sea level will drop, won't it? So at present, glaciers contain about 28 to 35 million cubic kilometers of water. And now all that water comes from the oceans. Okay, so during the maximum Pleistocene glacial extent, the number was approximately 70 million cubic kilometers. So you can see that's a lot more water, has been removed from the oceans. So this would have been enough to lower the ocean sea levels by about 120 to 130 meters for around 20,000 years. So that is a pretty big amount of water. Lost. That's a pretty big drop in sea level. So if we look at this diagram here, what can we see? Well, here's the sea level relative to modern. So 0 is the present day sea level. So plus 20 is the sea level goes up, and all these negative figures is saying the sea level is going down. So what do we notice? Well, okay. So right here we have the Wisconsin glacial period. So if you remember, that was the most recent one. Okay. And here we have an Illinoisan glacial period right here. So what you'll notice is, here we go, glacial period, all of a sudden sea level plummets down, doesn't it? Not really a huge shock there. As soon as we enter an interglacial, ice melts, sea level goes up. And then as soon as we enter another glacial, sea level goes down again. So not really a huge surprise there. So there's a little bit of a blurb here about archaeology in the UK, but that's not really that important. Okay, so if we melt all the water held in glaciers at the moment, it's going to see a sea level increase of about 70 meters. That gives you some idea of what can happen. Now, another effect of the glaciation that we see now is something called isostacy. So if you remember, we've discussed how the weight of the ice would push down the continental crust. That's all it is, just the sheer weight of the ice can do this. So obviously once the ice sheet is removed, well, the crust is going to naturally just bounce straight back up, isn't it? Well, yes, but that bounce doesn't happen quickly. The bounce has been happening over, a very, very long period of time, tens of thousands of years. So if we look at this map here, this is a map that shows us the isostatic rebound of northern Canada. So essentially 100 is essentially the area with the greatest rebound, and down around 10 and 0, that's the area with the least rebound. And so these areas, number one, is showing us, well, these areas were definitely covered in very thick ice, weren't they? So that's what's causing the isostatic rebound. It's just simply the removal of the weight, and the crust is just popping back up. Okay, so the weight of the glaciers pushed some areas about 300 meters below their pre-glaciation level. So that's a pretty substantial, drop. So, and essentially its effects can still be seen now. So when we jump to the next page, what you're going to see is you're going to see a beach, and it's going to show you the indications of the steady rise of the beach. So here we go. So here's a beach in Nunavut in Canada, and you can see these lines give you an indication of the beach slowly but surely rising relative to the sea. So this beach, this would have been the beach, I don't know, a few, maybe 1,000 years ago, and over the thousands of years, the beach has steadily been getting lower and lower and lower as the area of land here rises up. So this is a map here, shows you global isostatic rebound. So you'll notice most of the isostatic rebound is focused in northern Canada and the northern islands of Canada. We get quite a lot in Northern Europe, so Scandinavia. We also get a little bit in the United Kingdom, and we get quite a bit over here in some of the random little islands that we get north of Russia and north of Norway. In terms of the United Kingdom is actually quite an interesting case, because in terms of where we have the ice thickness, you can see we have a lot of ice thickness in Scotland here. When you look at the colour of it, the ice would have been somewhere in the 300 to 400 metre range, so thick, quite heavy ice, and it's pushed down the crust. And so Scotland and a bit of northern England and some of Wales were areas which were suffering depression. They were pushed down by the ice. Now obviously that ice has now disappeared, and so over the last few thousand years the United Kingdom has literally been popping up. So the northern part of Scotland, northern England and Wales are literally rising. That means that the southern part of the UK is actually sinking. The entire United Kingdom is acting like a giant seesaw. As Scotland rises, the southern part of the United Kingdom goes down, which I think is quite fun. That's quite a good part of geology. It's quite interesting. So the final few things we have to think about are what's happened to the water that was produced by these glaciers. Well, the water from the glaciers are going to form lakes. That's not really a huge shock. So these lakes are referred to as pluvial lakes or ProGlacial lakes, depending on where they're located. So during the Wisconsians, that's 85 to 11,000 years ago, many now arid parts of the US, especially in the southwest United States, had large lakes. So we've discussed how this area essentially became temperate, and the water coming off the glaciers produced very, very large lakes in this area. So it would have been an area of forests and grassland and large lakes. It would have been quite a pleasant place to be, actually. Now, the lakes that form away from the glacier are referred to as pluvial lakes. Okay, so they're distal to the glacier; they formed away from it. So their existence is a reflection of the cooler temperatures and the movement of the temperate zone south and the resulting cool, wet summers. So you have essentially ice melt, giving water to the area, but also you have water provided by this new temperate climate, helping to make the lakes as well. So just to give you some idea, by the way, so this is Great Salt Lake here, and you can see this would have been the size of the lake during the Pleistocene. So we had some huge lakes here. So a classic example of a pluvial lake is Lake Manly. So Lake Manly is right here, just on the California border. And it's now located in Death Valley. So bit of a change in climate, eh? So we can see the lake itself was around 145 kilometers long and about 180 meters deep. So it is a pretty substantial body of water. And the lake has evaporated away, leaving evaporite deposits. Now this is a false color image, but you can see here these areas which are whiter, and the blue areas represent water, water that's left, and the whiter areas here represent the evaporites formed by the evaporation of this water. And if you were to go all the way along, the valley, you would see just a constant sheet of evaporites produced as Lake Manly went and evaporated away. Now, in contrast, ProGlacial lakes are going to form right next to the glacier. Okay, so here we go. So these are the ProGlacial lakes. Now, typically there will be something about the terrain that will stop the water escaping. Okay. It could also be retained by a moraine. If a moraine is good enough, it can retain the water behind it, so forming a lake. So ProGlacial lakes will have sediments deposited in them directly from the glacier. So that means you will have a mixture of muds to gravel, so quite a big range of sediments, so quite a poorly sorted range. Now the muds form what we refer to as bands which are light and dark, and they're called varves. So the light bands represent spring and summer, and the dark bands represent fall and winter. So if you look at these lake sediments from the ProGlacial lakes, you can see these light bands, dark band, light band, dark band, light band, dark band, and that's formed by the very, very fine muddy material. So as you say, these are the proglacial lakes here, and they essentially form along the glacial margin. So in terms of proglacial lakes, the best example are the Great Lakes. So the Great Lakes, pre-Great Lakes, the region was an area of lowland cut by broad meandering rivers, so it was very flat terrain anyway. So when the glaciers came over, once again, they eroded the area. So any vegetation, gone. Any soil, gone. So the glacier is moving straight over the bedrock. But what does it do to the bedrock? Well, it doesn't just move across it. It grinds at it. It forms a depression, doesn't it? It slowly grinds away at the bedrock and actually destroys it. So an area which was here, all of a sudden is now down here because the rock has been removed. So it's now lower. The other interesting thing is that the glacier can actually cut below the base level. So if you remember, the base level is the lowest possible level a river can cut to. Okay? So a river can only cut down to the base level, and the base level is normally sea level. Okay? When a glacier moves across an area, on the other hand, it can actually cut below that base level. So it can effectively cut below sea level. So that means that any river in the area, instead of flowing towards the sea, will actually flow towards that depression instead. So that's why all of a sudden you get rivers flowing into the Great Lakes, producing the Great Lakes, because they're a natural depression in that area, which is lower than the base level. So water naturally wants to move towards them. So if we look here, so as the ice sheet retreats, obviously the ice water helps to fill the lakes along with those rivers, which are now channeling towards them. And the lakes have been reworked to some degree by a bit of isostatic rebound, because obviously once the ice is gone, the area is springing up. Not a huge amount, but it is springing up, and that is going to affect how the water is distributed. So if we just get rid of this here and have a look at the diagram behind, here we go. So a very simplistic diagram, but 14,000 years ago, here's the ice sheet over the top. Now remember, this ice sheet is gouging into the bedrock, okay? It's cutting down below base level. So it means the area of terrain here that's covered by ice is going to be below sea level, okay? So that means water is going to naturally want to flow into the lakes. So around 9,000 years ago, obviously, the glaciers are in full retreat, the ice water is filling the depression produced. 7,000 years ago, now there is going to be some isostatic rebound, which is going to affect the lakes. So we can see that some of the water is moving around in those lakes. Some of it is leaving a lot. Some lakes are losing a lot of water, some lakes not quite so much. And then around 4,000 years ago, we're going to see the lakes are now fully established. And we're going to see that once the lakes are full enough, water is going to start exiting them in the form of the St. Lawrence River and the Ottawa River. So the Great Lakes are a perfect example of these proglacial lakes. They're a wonderful example of it. Okay, all right, everybody, that is it. So please don't forget that code word. That code word was Africa. So take care.